So this is from Mr. Bean's homework 7.7, number 8. And so since this one has some domain range issues, I figured I would work this out for you guys. So we want to find the particular solution to the derivative equaling xy squared. And then they give us an initial condition there. And then they want us to sketch the graph afterwards. So what we want to do is we just want to do separable differential equation here. So I've got my dy, and then my y squared comes over to the other side, and then that equals x dx. So all I've done is I've separated all my y's and dy's to one side, and my x's and dx's to another side. Then we can integrate or anti-derivate both sides. Well, this would be the integral of y to the negative 2, which would be y to the negative 1 divided by negative 1, which is puts a negative sign there. And then the integral of x would be x squared over 2 plus some constant c. Now I usually go ahead and solve for c at this point rather than getting y by itself. I feel like there's less algebra to do that way. So this would be negative 1 to the negative 1 equals 0 plus c. All right, well, negative 1 to the negative 1 is just negative 1. And then that equals c. So it turns out that my equation is negative y to the negative 1 equals x squared over 2 plus negative 1. All right, and then at this point, we can try to solve this for y. And so basically, I'm going to take the reciprocal of both sides. So that's negative y, the reciprocal of y to the negative 1 is y to the positive 1. And then this would be 1 over x squared over 2 minus 1. And then if I multiply both sides by negative 1, I get that y equals 1 over 1 minus x squared over 2. All right, so we have a domain issue here because we need to see when this function does not exist. All right, so that doesn't exist when the denominator equals 0. So when does 1 minus x squared over 2 equal 0? Well, that would be when 1 equals x squared over 2, or where x squared equals 2, which would mean x equals plus or minus the square root of 2. Which, is about 1.4-ish or something like that. We'll put the approximately equals there. So that means that here on my graph, around 1.4-ish, I am going to have a vertical asymptote. Well, the negative 1.4, and then at 1.4 as well. We have to remember the behaviors of functions at that point. So we know that 0, 1 is a point on the graph. So we have a point right here. Well, if we follow these slopes, it's going up like this, but it can't cross that vertical asymptote, and then it goes up like this, and it can't cross that vertical asymptote. All right. So now what is it going to do on the other parts? Well, if we go back down here and look at our function again, it turns out that we can take the limit as x approaches negative infinity and the limit as x approaches infinity to see what's happening with our end behavior. All right, and if we do that as we head to negative infinity, we have a really, really, really large number there. So 1 divided by a really, really large number, we're going to get 0, and then here we're also going to get 0. So out at the ends, it's going to be heading to 0. The only question is are we up here or are we down here? And what we can do is we can just plug a number in to see. So let's just try to plug in the number negative 2. All right, so if we plug in negative 2, x squared would be 4. Right? And then that would be 1 over 1 minus 2, which is negative 1. So in fact, we are down here. And then if we did the same thing for positive 2, we would also get negative 1. So that means it follows this right here, right? Because we have a horizontal asymptote up here, and we have a vertical asymptote here, and then we get the same thing right there. And then so that's how we kind of know the shapes for this graph.